Thank you very much, Greg. I appreciate it and appreciate having me on to DroidCon Online. Yeah, the topic of this presentation is going to be indoor locationing. The title was my attempt at search engine optimization. It's not something I'm great at. Hopefully, I'm better at presenting indoor locationing. A little bit about me, not too much though, because well, that's not the interesting part of the presentation. Just why should you listen to me? I work for Zebra Technologies. We're a ruggedized Android manufacturer. We're an OEM for Android. And we produce the kind of devices that you might have seen when you're shopping indoors, or when the postal carrier delivers an object, a parcel, if you will, to your house. They'll typically be using one of our devices. And one of the things we've been doing lately is to try and make our devices more useful in warehouses where it's useful to know the location of the device or of the employee. And so we've been speaking with access point manufacturers and also making sure that we're able to support new location technologies. And so I thought I'd come and tell this audience more generically. This is going to be the only slide on Zebra. It's not like a sales pitch. I'm not a sales guy. I've been told I'm not very good at sales. I'm more better on the technical side. So yeah, please bear with me. So the experience of indoor location is complex, to say the least, and it's kind of suboptimal as well. And I started the thought of this presentation was like, what would actually happen if I said those magical words to my phone? Turn the light on. If I say that to my Nest or whatever that thing's called by the side of my bed, if I say that, it's going to turn on my bedroom light. The Nest thing knows where it is, or the Echo Dot knows where it is in the house, because you've told it what room it's in. If I say, turn the light on to my phone, it tried its best. It actually ended up turning on all three of my IoT connected lights. So it knew. I mean, it didn't even know I was in the house. It kind of made an educated guess. Hey, these are the only lights I know about. I'm going to turn them on. It would be a better experience, I think, for my Android to sort of know what room I was in and then turn that specific light on. So how would you go about adding indoor locationing to an Android device? And this is not a new problem. In fact, the problem itself goes back way before Android. And the market is suffused with different solutions that are available, and there's different technologies which underlie these as well. There's Bluetooth Low Energy. I think everyone's familiar with BLE beacons. You plop the BLE beacon on the side of a shop, and then you're near McDonald's or whatever it is, or you're on the third floor of the mall, that kind of use case. There's RFID tracking solutions. Like, we've got a whole business unit that's concerned with tracking the location of players on an NFL field, which is some form of American football. I'm told. I don't get too involved in it, but it's very exciting that we're involved in that. But that's using RFID. Cisco routers, if you're using those, they have like a proprietary system for monitoring your location based on the time of flight of the networking signal, like using all sorts of complex geometry from their routers. And things get even more innovative as well. There's a company, I think it's Mist, that's able to almost project a BLE beacon into a particular point, so you don't have to manage all this infrastructure, and they do that from a different location, an access point elsewhere. We've also dealt with another company, which I think is Signify. It used to be like Philips Lighting, where the device's front-facing camera is able to determine which light fixture it's immediately underneath. And so, like, hey, I'm underneath this light fixture. This light fixture is in the bedding department, and therefore, I know where I am in this particular shop. All very interesting stuff. However, the sort of underlying complexity here is all of those technologies which I spoke about on the previous slide. They just tell you, the BLE beacon gives you an address of where you are. It's not a physical address, it's a string, isn't it? Or I know I'm under this light fixture, or I know I am sort of within range of this particular access point. The real intelligence is converting that information into like an actual position in the shop or in the warehouse or in my house. And so there's always going to be, and this is just something I Google imaged indoor location system. So this isn't like a sales pitch for any of these technologies. There's always going to be this mapping component that actually presents the user's position on a map. It might be on their device so they know where they are, or it might be at some back-end service somewhere if you're trying to track items within a warehouse, like an aircraft manufacturer, for example. There's some quite expensive part bins, and so you want to track where each of those bins are at any time. Just one use case. There's obviously loads of these. But all of that is like the background to one of the new kids on the block, which is the Wi-Fi RTT, and it goes under various names. There's the IEEE standard 802.11mc. I've also seen it called FTM if you read the Android docs. No, the Android docs, sorry, is Wi-Fi RTT. FTM was the Wi-Fi Alliance name for it, but it's all talking about the same thing. Similar to what I was mentioning with that Cisco technology, where you're measuring the time of flight of the signal, the propagation signal from the access point to the device. Well, here it has like a standard implementation, and you're measuring the time that the signal takes to get from the access point to your device. Your device can then knows how long it takes to turn it around. It knows how long it takes the signal to go back to the access point. And all of these timings involved, I'm trying to describe the diagram on the right in case you couldn't guess, are resolvable to the nearest 1 nanosecond, allegedly, which gives you a potential resolution, if you work it all out, as 0.3 meters or a foot. So that's the theoretical limit of the accuracy that you're going to get indoors, which is, I mean, it means nothing because I'm on a camera, but that's really good. That's the difference between, not just between which aisle I am in the shop, but also like whether I'm looking at the socks or whatever's next to the socks. I don't know, the shorts in the shop. You know, I can really track very accurately where anything is indoors with that kind of 1 foot resolution. You don't get that in real life. That was spoiler alert. I'll go on to that in subsequent slides. So this technology is first really came into the public perception in about 2019 when Android Pie was released, and it had inbuilt support for Wi-Fi RTT. And if you're anything like me, then you thought, hey, this is really great. I'll download the sample. I'll have a play with it. It wasn't the easiest of things to kind of have a play with and get up and running with. You need to have 3 different technologies in order to actually implement a solution with Wi-Fi RTT. First of all, your access point needs to support it. And when it was first launched, there was like 2 that supported it, and it looked like a bit of a dodgy, I'm sure it wasn't a dodgy website, but it wasn't like Amazon that you could buy these things on. Other websites are available. You also needed to have support in your Android phone. Android Pie, any Android device running Pie, that was the marketing blurb with, hey, now you have Wi-Fi RTT. What wasn't so obvious was you also needed to have support in the underlying network stack on the phone. Now, this was back when I had a Pixel 2, which the dog has eaten by now, but it worked on the Pixel 2, but we had I can't show that, we had like these devices, they were running Android Pie at the time, and they didn't work because they never had the network stack support at the time. So what's changed? Obviously, we're not in 2019 anymore. We just look back at those years through rose-colored glasses, I think. What's changed is, and this isn't just me making guesses, you know, I've spoken to some of our sales guys. We have like a networking division sort of to get their feedback on some of this. Understand, first of all, I'm talking about support in the access point needs to, somewhere in the access point needs to be there. Most access points will use one of 2 system-on-chip providers. So they're either going to be Broadcom access points or Qualcomm access points. And I'm told, via reliable sources, that both of these Broadcom and Qualcomm vendors have had 802.11mc support in them since 2018. Which makes sense. That kind of aligns with Android coming out with Pi, supporting. So what gives? Why didn't we have all of the support out of the gate for the access points? The problem was at the time that there was resistance in the AP manufacturing industry, that they didn't want to enable this because often it would be in contrary, that's not the right term, to their own proprietary solutions. And That has started to change. Access point manufacturer opinions of things are turning around, mostly driven by the desire for big companies like who are going to buy thousands of these things across their hundreds of stores or warehouses or whatever industry you're in, to sort of undergo a hardware refresh. And when you get these requirements that come in from these big companies that people like Aruba listen to, then they're going to have their requirements. We want Wi-Fi 6 is a big one. And also, hey, wouldn't it be great if you could enable 802.11mc? So we've partnered recently with Aruba to make a big announcement. And we also said that Aruba support this technology, and we would see other access points supporting this in the near future as well. So that's where we see these things going. The other change, of course, that's happened originally when it was Android Pie, very few phones supported Pie, obviously, but now I took this screenshot a couple of months ago, I think it was, and Google was saying that 340 Android phones support the indoor location. So that includes the network stack, obviously. This list will be growing all the time. All of our latest devices support it. I'm sure our competitors' devices do, as well as many consumer devices. The access points, though, when I took this screenshot, the Nest router supports it now, but it didn't support it at the time. So again, we see this rolling out into access points, and that list will eventually grow. My attempt at a meme. I know I've been talking for a long time, so I do like to try and demonstrate this stuff. When I first come up with the idea for this presentation, I was going to be on a stage, and my colleague was going to be behind me, like moving a phone around. Obviously, I don't live on a stage. My life is a stage, isn't that an expression? But it's not for my life. Anyway, what I want to show you is. And I was surprised that the team let me show this publicly, but here we go. We are demonstrating this with one of our retail partners, and we wanted to show them exactly what you can do with this technology. So we're not even using our hardware here. We're using a Google Pixel. So this is something you can do at home if you have a simulated retail environment at home. There are 6 Google Wi-Fi access points in this demonstration. There's been some assumptions made about the height that these access points, well, no, we know where the access points are, but the height of the user and how they're holding their phone, how we're triangulating the position. I'll get into the calculations in subsequent slides, but I want to show you here the accuracy that we're seeing. I mean, it says 1 meter. Remember, the theoretical limit was within like 30 centimeters. Well, now this is our internal team saying that they can get it down to 1 meter. Simulated environment. So I think it's a lady is walking down, and on the left there's like our company logo is showing where we perceive that user to be, or their user's phone to be, more accurately, calculated based on Wi-Fi RTT. So notice how it got a little bit confused when she got next to the wall at the bottom, but now she's sort of away from any surfaces. It's tracking her quite well. It has a good line of sight to this person in this open environment. I think it gets a little bit confused in a minute. Yeah, it's kind of jumping around a bit because she's gone near a shelf, gone around a corner. The access point can't see her, but now she jumped into the corner there. Now it's fully visible. And notice she stood still. There's a little bit of jittery in the logo on the left, trying to determine where she is. I mean, she's turning around. We don't have that compass sensor built into this demonstration, but the idea there was to just show that the technology is kind of getting there. I'll get into some of the restraints here, but just bear in mind that was like an almost open plan area. It wasn't open plan. There was shelving, but when she was in the middle of the aisle, yeah, you could see that she was walking up that aisle quite reliably. And 6 access points, quite dense coverage in that kind of area. Let's talk about the APIs now. Let's move on to the device, and this is what Android offer the application developer, which is most people on this call, I'm sure. So there's a class, Wi-Fi RTT scan. That's the sample app, I should say. So the APIs there's a Wi-Fi RTT manager that allows you to create objects and initialize the API, do all that kind of factory stuff. Well, it doesn't use a factory pattern, don't worry. Then there's the ranging request, where you can actually, what is this? You can build, like you can say, I want to range off of this particular access point. well, this is how you build the request. And then the result is where Android tells you this is how far away you are from the access point. So I just want to be clear. You're telling Android, this is the MAC address. I'm going to say MAC address. I think we all know of Android sort of, cutting down on MAC, whatever. We'll say the MAC address. This is the MAC address of the access point that I want you to get the distance to. And Android will return to you in that ranging result, the distance in meters and its degree of confidence in that distance in the form of, what's it called, standard deviation. That was added in Pi. In Android 10, and there's been no changes in Android 11, nor I can see any changes being made in 12. So in Android 10, they added what they call response location, responder location, civic location keys. And this enables you to read from the access point, where the access point supports it, the location information which that access point reports. And I've got that on a subsequent slide, so I won't go into detail of that, but just bear in mind that that API was added in Android 10. If you take a look at the sample apps, this has changed. Would you believe it? I put this slide together, a few months ago now. It probably was, because I like to prepare for these things in advance. And the actual sample app that was available from the Play Store looked different to the sample app which was available in the source code repository. The Play Store was more up to date. So if you tried to do this like I did a few months ago, you might have noticed that discrepancy. If you do this today, then both the sample code and the Play Store app will be the same. But this is what you would have seen a few months ago if you tried to access this. I find this a little bit easier to explain and understand, to be honest. I'm going to be one of those people that uses the laser pointer. I'm sorry. But the first thing you do is you sort of ask, are there any APs nearby that support Wi-Fi RTT? And in this example, there's 3. When I was doing this myself, I was using up to 4 routers, so they're returned here. You then click on a router, and it will give you the range in meters and the standard deviation to that range. And there's a couple of other things you can select in this sample app, and they're still there in the new version of the app. It's just the UI is a little bit different. The key takeaway here is that by default, it will kind of make a request every second, and that's not the best way to get the most accurate results. Like, obviously there's going to be a power consumption consideration, but the more frequently you ask for a ranging result, the more you're able to sum up the user's location, particularly if they're moving. So let's say you make 1 ranging request, you just have that one piece of information. If you make 10 ranging requests in a second, then that's more information. You can take the average, and you'll have more confidence in your distance to that one access point. This is just a few screenshots of what that looks like. If you run the latest sample has made everything look a bit nicer, but it's also added the LCI, the location, the things that were added in Android 10, the ability for the access point to report back to you its location. See here, it's reporting a specific latitude and longitude. So yeah, there's also the ability to log this stuff, because just displaying it on the screen isn't that helpful. What I actually found when I did my own testing, and this is what I wanted to show now, I'll just show this very quickly. So I wrote a sample app that was largely based on that previous the Google sample, but I just wanted to, you learn by doing, don't you? And the idea here was to, there you go. So it's detected 7 access points. And then I think I select that I want to get ranging every 10 milliseconds, and just give me the average of the last 5 results. And after I do that, the video's going a little bit funny on me here, but it just emphasizes my point that it's best to make many requests, and then you get a more accurate location. I think that's all this video is going to show, actually, but I'll move on. So having got the distance to one access point, that's all very well and good, but I know how far away I am from the access point, but that's all I really know. And then it's up to me as the application developer to convert that information into a consumable thing that I can give my user. So there's a couple of ways to do this. The first thing, I don't know why I keep dwelling on this point so much, but it's best to use a weighted mean calculation. So you could, and this is what the sample app does, just add up the like 10 distances a second, divide that by 10. That's my that's my distance from the router. You also have the standard deviation returned as part of that API. So use the weighted mean, and enables you to include the standard deviation, gets you a more accurate guess of where your user is or how far your user is away from that access point. And then having done that to one access point, you know that the user is within sort of a circle of a single point, and you probably know where I'm going here. So they could be anywhere in this in this circle. Now, if I range off of a second access point, I can do some calculations. And let's be honest, we're talking theoretical in an ideal world here. I now know, because there's two intersections with that other access point, I now know I'm at one of those two positions. I can then locate off of a third access point, and now I can reduce that to myself being in a single location. In an ideal world, I mean, when you do this in practice, you'll find that the actual distances to those three access points won't give you a nice single point that you are at, but we'll get to some of that. But so in general, in order to locate yourself in a two-dimensional space, you need 3 access points. If you're dealing with a 3-dimensional space, and this was my attempt to do something that looked pretty and I failed horribly, but if you're trying to find yourself in a 3-dimensional space, then you need to use 4 access points. Now, if you're going to do this in 3-dimensional space, then the first problem you'll come up against is like signal attenuation. Like how are you going to accurately measure the distance of the user to access points when there's stuff in the way? Because there's probably going to be a floor in the way if your access points are at different heights. Just saying. In which case, the distance through the floor is like, I don't know, that's going to harm your calculations. So, and we'll get to that when we talk about the problems with some of these approaches to the technology. I got a little bit lost when I was trying to do that whole calculation of where am I based on these different points. I found this really great open source library. So full credit to the gentleman or lady who put this thing together. I'll put the link here. This enables you, this library, and my colleague also used this independently. This library enables you to determine your position as like a best guess, and I said that these things never return the exact numbers, and so you can even see the screenshot here from his README file. It's making a best guess you're somewhere in this vicinity. You do need to convert your you need to define a coordinate system, I should say, in order to pass into this library. So I think it uses like Cartesian coordinates. I got a little bit, I was doing my best, and you can't just give it a latitude and a longitude. You're not going to get that out. If you want to use this with latitude and longitude, for example, you had 3 access points and they were reporting their lat and long, you would need to convert those into what's it, WGS84. And I can tell when I'm going off on a bit of a tangent, so I'll stop now. This was the point where I was planning on doing the live demo when I was thinking about this presentation pre-COVID, but unfortunately we can't. And I do have a demo though. I did set this up in my study, so I'll show you what that looked like when I tried to run that. What I was trying to do though is to just show you all of the things that can go wrong if you're testing this yourself. And it's a combination of things that would happen in real life versus what would go wrong in the demo. And also I was trying to set myself up for, hey, if it fails, this is the reason. But I was using Nest access points. Like I would imagine if anyone on this call is going to set this up for themselves just to have a play with it, you're probably going to use these access points there. A couple of $100. So it's not, what they're like, I think they were less than $100 each, but if you're going to buy 3 or 4 of them, it's not like pocket money, but at the same time, it's not, you're not buying $300 routers or pound routers or euro routers, whatever country you're in. So they're being powered over USB. They're actually being underpowered, I think, for this demo because I didn't have enough plug sockets to do all this in a small area. They were way too close together. That's the real thing you want to watch out for. So the more access points you can range off of, in theory, the more accurate you can be with that that multilateration library to say, hey, I'm this distance from 5 access points, give me my actual position. But when you get that many access points that close to each other, where your phone can see them or your device can see them, then invariably there's going to be interference, and that's going to result in in incorrect values being returned from that API. And there's no real way for you to know as the application, like how accurate those values are, other than that standard deviation. And anything in the way is going to add signal attenuation to this whole calculation. So as an example, I just wanted to see what kind of attenuation I would have just by putting a door in the way. And I'll be honest with you, I live in a really cheap house. The doors, I could put my fist through them if I was that way inclined, but I'm not that manly. But if I could put a hammer through it, I'm sure. But my point is, when I did that, the readings went all over the place just by having a couple of thin bits of plywood in the way. So imagine what metal shelving does, or a whole floor of a house does to these kind of calculations, and the distances that you get back in the API. And sometimes my access points to stop working. But what I ended up doing was defining my own coordinate system. And I mentioned you could use the geodetic system, like you can convert everything to lat long. Easier to talk to other applications, but it gets a little bit confusing, particularly around height and sea level. And for me anyway, maybe you guys are really not like me. So I just decided to define my own coordinate system and just said minus 2000. I worked it in like 1 unit is 1 millimeter. And I wrote a little sample application. It's available on my website here. I used that library to sort of show me where I am, and I tried to draw these things on a map. I think what I actually did in my personal sample is I had a diagram of my house that I managed to get from when I bought the house from the estate agent. They give you like a floor plan or whatever, so I put my location on the floor plan. But obviously I didn't want to put that in GitHub for the same reason you don't put Bitcoin wallet keys in GitHub. But here is the results that I was seeing in my sample app. So a couple of things to point out. The video is going a bit funny again. It's jittery. It could really do with going through some kind of smoothing algorithm. And the video is going a bit funny. I apologize, but I'll just describe what's happening. You really want to smooth these values before you put them onto the screen. Run them through a Kalman filter. The video that I showed at the front of this presentation, where it had the person walking through the warehouse, that data had been put through a Kalman filter to smooth out some of the visual elements of that. I was in a line also. I wasn't like going in front or behind these access points, but when you can get more accurate results off of your access points depending on how you've distributed them. I found out after I put this together that having them in a line, which is all I can do in this room, was the very worst thing you could do. I even took these things out into the garden, but my garden slopes down, and then I had the problem with height. And I'll save you the effort to realize that as soon as you get off of the perpendicular, off of the parallel, whatever, with these nest routers, the calculations go all over the place. Like I was, let me try and do this on camera. Like the access point was here, my phone was here. If this was reporting 1 unit of distance, I would move my phone up, and hey, that's the hypotenuse, that's Pythagoras. You'd think the distance would go up, but no, the distance actually went down that it was reporting, and that was with a Pixel 2. I never actually tried that result with my, I've got a Pixel 4, I think. Now I can't keep up with the numbers, but anyway, so that's some of the pitfalls that I found when I was implementing this. I did have this slide here. I wanted to talk through some of the more detail, excuse me, some of the detail of the change that was added into Android 10. You might have seen if you read the release notes, hey, Wi-Fi RTT has been improved. What it does is it is possible to configure some routers, not the Nest routers, because they're not like industry routers, but it is possible to inject location information to a router. And this information could be latitude and longitude and altitude. That's kind of most useful if you're thinking of sort of comparing that with a world map or Google Earth, for example. Or you could put all sorts of information in there, like, I thought I had them on this slide. I do. I have them on the next slide. Things like city, country, building, desk. I'm getting these from the API, incidentally. So you could program the router with this information. And then the API in Android will read this information and report it like it would trust it. So you could put anything you wanted. You could say you were in San Francisco, but you're actually in Basingstoke, which is where I am at the moment, and you can just pretend that you were on holiday. But no, it's so that you're going to know that you are X meters away from any of this information, or you're X meters away from a latitude and a longitude if you've programmed it with that. And then you've obviously got like the challenge of then converting that distance into a format that you can that you can like then use in the multilateration and all sorts of the height considerations. It is possible to do. It just gets a little bit, it's more complicated than using the fused location provider. I think that's in one of my conclusions here. So in the sort of conclusions that I wanted to go over, it's an interesting technology, and it has been an interesting technology since it was first sort of made publicly aware in Android Pie. But the results that you're going to get from any kind of implementation are nowhere near the 30 centimeters stated like theoretical maximum. Like my colleague that worked extensively with our partners on this was saying about a meter for sort of sales purposes. What I was seeing was a meter is being quite generous. You're probably looking at a little bit less accurate than that. But if that's okay with you, like I said 30 centimeters, that would be the difference between I'm looking at the socks or I'm looking at the shorts was my example. Whereas a meter, like the standard run of shelving in a shop is a meter. So I mean, that's the difference between looking at the lamb and the pork, for example. So maybe your use case is fine with that. It's better than some. There is more work for you to do as the application developer, potentially. A lot of this stuff could be done on the back end. So maybe the application is just reporting up to some back end server somewhere that I know I am 5 meters away from this access point. Maybe I can use that in conjunction with other information. Maybe there's a BLE beacon on that floor, so I only range off of the access points that I can see that are on the same floor as me, and that gets away from the height consideration where you can't range through the floor that you're on. But having said that, any solution needs support from both hardware and software to make a generic deployment practical. You need the access point, you need Android, because I did look it up like a couple of weeks ago and it wasn't in iOS, I'm sure, when I looked it up, and I'm pretty sure it's not there now. So this is an Android-only technology. So you couldn't really roll this out into a consumer where consumers are going to come in and use this in your app. Maybe in sort of my field where we have dedicated devices, people are walking around, we know they're running Android, but yeah, lots to consider. Certainly a lot more complicated for you as a developer than the fused location provider, where I mean literally that thing's just magic, isn't it? You give it one call and it will return you a latitude and longitude, and you can look that up on a map, and Bob's your uncle and someone else is your aunt. Conclusion. So yeah, we've partnered with Aruba. Other Wi-Fi AP manufacturers are coming on board with this technology. I did just want a final word though to say, don't take my word for it. I like to do this in my presentations where I can. I discovered this paper after I'd done all of my investigations. So wouldn't it have been nice if I saw this before? But yeah, this gentleman out of MIT, so you know he knows what he's talking about, did this same kind of investigations as I was just describing, like, hey, what is Wi-Fi RTT? What use cases would it be useful in? How does it stand up in a real situation where there's buildings and floors and walls and all sorts of other stuff in the way? And just to sort of make a couple of things clear from his abstract, he agrees that you're not going to see a better accuracy than 1 or 2 meters standard deviation in sort of range there. You're really limited where it's open sort of environments, and you need to understand all of these sources of error, like I was mentioning my door, that or coming off of the horizontal where the distances just went all sorts of wacky. So good if your use case is okay with not being 100% accurate and all those other considerations. So with that, I've come to the end of my presentation. So I've put resources here. I'm sure the I'm sure the links, the code, I'm sure the slides will be available after the presentation. And I've got a slide for questions now. So I guess I go to the questions box, which I'd previously hidden until now. And then, so I'll just go through these. So has the talk started? Yes, it has. I won't read them all out. May you share the presentation? Yeah, so all of the, I don't have any problem with this presentation being shared, Greg. So I guess that you put this online, but I will also have this on my website if I'm able to do that. The link was at the bottom of all of the slides. So are you supposed to be two? So are we supposed to be 2 meters apart from each other? That's yeah. All right. So interesting. There's all sorts of systems, aren't there? But yeah, Google went with the old Bluetooth technology, didn't they? And so to detect if you were 2 meters apart or not. With and Apple did the same thing. They were using Bluetooth with the NHS app. It is in the UK. What's the actual name? Where the health, the COVID apps, all of those. Guys. Oh, thank you very much, Aristos, for sharing that. If I don't have the slides up yet, I will put them up at the end of today. There's more Q&A. Oh, sorry, I'm looking at the chat window. Oh, I'm so sorry. Okay. Just proving that I'm. So, do iPhones and iOS support 802.11mc RTG? No, they don't. Is the quick and dirty answer on that. And I think that's really what's holding up the adoption. To be honest with you, I mean, I'm an Android developer. I have been since Android Gingerbread. So I'm more knowledgeable about this side. But yeah, that's it's been a bit of a tricky thing for the technology not being supported on iOS. Does it have any influence on the accuracy if the user's body is placed between the phone and the access point? Yeah. So I don't remember doing that test for myself, but anything that was placed in the way, really, it wasn't even predictable. Like sometimes I would test it and it would be reliable and not reliable. It would be like more, and sometimes I would test it and be less. It would just be less accurate if there was something in the way. So how is the accuracy with different smartphone Blue Pixel and accuracy similar? Like I say, I did this test with a Pixel 2, and I've also done it with a Pixel 4. And my colleague has done it with, I mean, these are our sort of enterprise devices. This is a TC52. We've all seen very similar accuracy readings. I would say that I and my colleague always use the Nest access points because they were just easily obtainable, and you could get like 4 of them for an amount of money that we could expense without causing too much stress in our managers. Whereas like in industry, obviously there's different access points. You might see more accurate results, but I can only talk to what I have tested with. So will ultra wideband, such as on some iOS devices, be a better positioning solution, or is it more complementary? So the UWB, we have a whole I talked about our location division briefly when I said that we monitor the position of the NFL players on the field. And one of the things that our location this is where the radar things go, by the way. That's why I'm doing this. I'm not pretending I'm a football player. It's a complementary technology. It couldn't replace it, but maybe it could work in tandem. I think UWB requires, and I've not actually done this myself, so hopefully I'm not speaking out of turn, but it requires more infrastructure, more setup, and so. But it can be quite accurate once you've invested in that setup. I think indoor locationing technologies in general are the more money you put in, the more accuracy you get out. So that golden sweet spot is maybe 802.11mc was a cheap version to get really accurate locationing, but it didn't quite work that way. If, I mentioned earlier on, that use case where you were trying to track aircraft parts, these things cost thousands of pounds or dollars or whatever country you're in. And they will invest in a beacon on every single box or part so that you have absolute location of where that item is, and all sorts of radar sensors. But anyway, back to the Q&A. Can we assume that the processing times on the phone or the access points is a constant or consistent, or can they constantly change? So talking about that diagram I had on one of the first slides, where the request you have the request from the access point, and then you're sending the response back to the access point, or maybe it's the other way around. There's going to be some time where you're processing that in your phone. You don't have to worry about that as the application developer. I was trying to find a good way to say that, because all of the considerations around what is that latency is taken care of for you by the underlying implementation in both Android Pie 10, 11, 12, whatever it is, and your network stack on your device. So that's why you needed to have the network stack and the phone all supporting this, so that it's able to handle that latency. So the minimum number of APs is 3, but ideally it would be 7 to 8. How big of a space can be tracked? Assuming Wi-Fi range is around 5 meters, say, with 7 access points scattered around, maybe with 15 minutes. Yeah, so I think your point you're sort of getting at there is, and this is one of the problems I had with my like my Nest routers. You can't really get more than 3 or 4 of them in the same space before they start interfering with each other, or you start losing them in your phone won't even try and connect to them because it will see like you've got too many or it's too noisy. Yeah, the more the better, but you start to get the errors that crop in because of the signal interference. That's what I'm trying to look for. So in my testing, I think the best test that I can talk about would have been that video I showed at the start, where they had 6 of those Nest access points. But if you had an industrial access point that was stronger, putting out stronger signals, then you could be further away, and then maybe you could range off of more of them at the same time, because you're able to see more and you have a wider distance than that 15 meters, like you say. Wi-Fi frequency 2 gigahertz or 5 gigahertz. I'm both. I think I've never seen anything that like compares the two or has any kind of constraints. It doesn't say it needs to be 5 gigahertz, for example. So that's a good question. I'm not sure, but I'm pretty sure it doesn't matter. Could you talk more about the limitations of beacon technology? I'm probably not an expert to talk about the limitations of beacon technology. I've not done any sort of sample apps with them. All I can really say is, like, all you're doing is getting the ID of the beacon that you're near. So you can there's a distance that you can be. There's like 3 or 4 different standards of these beacons, but from an API point of view, you know that you are near a beacon. What beacon are you near? You have a string, but what does that actually mean? And so what typically happens is you, the application developer, will send the information up to some server somewhere. I, whatever ID you are, am near beacon ID 4, 5, 6, 7, 8, and therefore it's up to the server to say, oh, well, now we know that Darryn is near McDonald's again. Get him away from McDonald's, and therefore it will send the server will then send a message back to the phone to say you are near McDonald's. You can't actually do that. I suppose you could do it on the device, but you'd need all of that information, and that's not how in the applications are typically architected. Can you mention the name of the test up on the Play Store? I don't have time to build from the GitHub repo. So the name of the test app, and I'll go back to it because I don't want to give an incorrect answer. But I'm sure if you search for Wi-Fi RTT, it will be there. And you're looking at, so that's the actual link. So it's Google Android apps location RTT Wi-Fi RTT scan, and wow, that just takes you to it. So yeah, I mean, it was there last time I checked. I can't imagine Google would have taken it down at all. The screenshot will look. I've literally taken these from the README files. So if you see these images, then you know that you're looking at the right place. Which Zebra devices support 802.11mc? Oh, I didn't want to make it into a sales pitch, but since you ask, all of our latest devices running Android Pie or above will support it. So I mean, if you had a particular sales question, then reach out to me or whoever offline, and we can certainly help you with that. But I mean, I've got a TC52 here that supports it. We released it about a year ago now, so maybe more. So certainly any of our recently sold devices support this. It just has to have that network stack. It might even be upgradable on older devices, but if you had a particular model, then I could check offline, but I don't know off the top of my head, I'm afraid. So within our office, we use specific beacons positioned on each floor all over the place, and it powers our custom app to locate us on each floor reasonably accurately. What's the benefit of this instead? So if you have that technology, I think I've sort of covered this in other answers, but those beacons would probably tell you what floor you're on. It might tell you what room you're on, but it might not tell you whereabouts in the room you are. Honestly, in an office environment, 802.11c isn't probably the way to go. There's too much stuff in the way. And I know my colleague found this. I used to have a previous demo he did, but he was like going around the desks, and it made me laugh because it looked as though he was climbing over the desks. So I was saying to him, well, you must have been really annoying Miriam when you're climbing over her desk there. But in actual fact, obviously he was walking around her desk, but it wasn't accurate enough to sort of track him in that way. So my question is also about variability in the processing times on the router due to congestion. Can that be an issue as well? Not in my experience. I think if the router claims to support 802.11c, then that is handled for you. I've never read that, and I read that like paper as well by the professor at the MIT. I never like read that was a consideration. So no, not as far as I'm aware, the answer to that question about the processing time on the access point. And then how much is the distance measurement stable in time? That's a good question. So this sample out here, for example, and I know the video kind of went a bit poor, so this wasn't obvious in what I was showing. But you could, if I make a request now, and then I make another request 1 second later, I don't move, the access point doesn't move. I was seeing variability of around half a meter sometimes from request to request, maybe even more, maybe like 60, 70 centimeters. And I was going to point at my wall over there. Obviously, you can't see how far away that is, but I was only about a room away from the access point. And as a result, that's why I say the more often you can make this query there, like if you can do that 10, 15, 20 times a second, then you get a more accurate result, because those outliers that were 70 centimeters too long, and then you've done another one at 70 centimeters too less, so you get the average. It averages out in the end. Obviously, you can only make those requests so quickly. You can only really do that if you're in the foreground, otherwise you're going to be draining the device's battery as well. And so yeah, I think that answers the question.